Section 2.1 goes into some detail on how floating point numbers are stored in computers. We're going to be using MATLAB for most of our programs, and MATLAB, everything's stored as floating point, even integers, and most languages integers are stored differently and exactly, but MATLAB doesn't have integers. Even integers are just floating point numbers that happen to be integers. And floating point numbers are stored in IEEE double precision format, which means the following. That's 64 bits, double precision 64 bits. The first bit just tells you whether the number is positive or negative. The next 11 bits store the exponent, and the last 52 bits store the mantissa. And let's get an example to see what that means. So let's take the number minus 12.25. How is that stored in IEEE double precision format, i.e. on MATLAB? And you first convert it to binary. The 12 would be no ones, no twos, 1 4 and 1 8. And the 0.25 is no halves and 1/4. If this didn't have an exact binary representation, this would keep repeating. So this number can be written as minus 1100.01 in binary. Now you convert the binary to normalized binary form. That is, you move the binary point, the decimal point, up to make it 1 point something. So every number is going to, the leading digit's going to be 1 for any binary number except the number 0. With decimal numbers, the leading digit could be anywhere between 1 and 9, but binary it can only be 1. So basically, you know that first digit's going to be a 1. So move the binary bit up to there. You moved it 3 places, which means you have to multiply by 2 cubed to compensate. Made this 2 cubed smaller, so you have to multiply by 2 cubed. So this is in scientific or normalized binary notation, minus 1 point something times 2 to the something. Okay, the 3 is the exponent. Well, the first bit is 1 because 1 means negative, 0 means positive. Then the next 11 bits store the exponent, but they don't just store the 3. You might think, I would have guessed that the next 11 bits just be one sign bit to tell whether the exponent's positive or negative, and then 10 bits to give the magnitude, but that's not quite the way it works, although it's almost equivalent. What's actually done is the exponent, 3 in this case, is added to 1023. So 3 plus 1023 is 1026, and that is written in straight binary notation in those 11 bits, which is 1024 plus 2. So this is the 11-bit binary representation of 1026, which is E plus 1023. And then the mantissa, 100100, all the rest zeros, is stored in the next 52 bits. And notice the 1 isn't stored because every number is going to have a 1 as the leading bit, except the number 0, which is special. But everything else, you know that's going to be a 1, so why waste a bit storing that? When you do some arithmetic operations, the computer will remember that there's a 1 there and it won't forget. But when it's just storing the number, there's no need to store the 1, just the part to the right of the 1. You know that's got to be a 1. Can't be a 2 or 0. So there's your 64 bits. So A has a 1 to first bit to tell you that it's a negative number. Then the next 11 bits is 1026. That's E plus 1023. The next 52 bits just stores the mantissa, and well, that's the way it's stored in the computer. We're going to print it out in hexadecimal form. If you printed it out in binary form, there'd be 64 ones and zeros, which should make your eyes hurt. So we're going to print it out in hexadecimal form. That's only 16 hexadecimal digits. Each hexadecimal digit is 4 binary digits, so that's easier to look at. So the 1100, that's 12. In hexadecimal, that's a C, because the hexadecimal digits are 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and 12 corresponds to C. And then the next 4 bits is 0 in hex. Next one is 2, and that's 8 plus no 4s plus no 2s plus no 1s, another 8, 0. So it should be C0288 and then a bunch of zeros. We'll try that in just a minute, verify that. Meanwhile, the exponent is stored in 11 bits after you add 1023 to it. Well, what's the point of that? Well, those 11 bits can store anything between all zeros, which is 0, and all ones, which would be 2047. So the E plus 1023 can be anywhere between 0 and 2047, which means E is between minus 1023 and 1024, which means 2 to the E is between 2 to the minus 1023, which is approximately 10 to the minus 308, and 2 to the 1024, which is approximately 10 to the 308, which means that our number basically has to be somewhere between 10 to the minus 308 and 10 to the 308th. If you try to store numbers larger than that, you're going to get overflow. If you try to store numbers less than that, you're going to get underflow. You just can't store numbers that small or that large. But since that's way more than the number of atoms in the universe, you're not likely to need numbers bigger than that unless you're making an error in your program. It's usually the only time that overflows is you've got an error. So that's plenty big for most all applications. And the relative precision, you've got 52 bits in the mantissa, so your numbers are stored out to 52 binary bits, so your relative accuracy of numbers that you can store is 2 to the minus 52, which is approximately 2 times 10 to the minus 16. That means you have about 16 decimal digits of accuracy in your double precision floating point numbers. There's also single precision, which only stores about 7 decimal digits, but MATLAB does everything in double precision. Okay, let's verify that the number minus 12.25 is stored as we claim. We'll switch to format hexadecimal and now print out A, and it does come out as we predicted, C0288 and then a bunch of zeros. And now we said we can't store numbers larger than 10 to the 308th power. Let's try 10 to the 300th power. And there's no problem. But you try 10 to the 350th power, and you get infinity. It just can't handle it. If you try numbers, real small numbers, like 10 to the minus 300, no problem. But try 10 to the minus 350, and it just says 0. It doesn't give you an error message. You know, that's so close to 0 that it says for most purposes we'll just change that to 0 and you'll never know the difference. So underflow is not as big a problem as overflow. If you have a number 10 to the minus 350th power, 0 is probably close enough. But if you have 10 to the plus 350, that just can't be stored. A typical test problem over section 2.1 is shown here. We've got a fictional computer that has 128-bit words, twice as long as IEEE double precision. And this fictional computer, you put the number in normalized binary notation. First bit is a signed bit, same as reality. But then the exponent is stored in 13 bits, and you add 4095 to it. And the mantissa is stored in 114 bits. So this computer is a whole lot more accurate than the double precision. Has 114-bit mantissa instead of 52, and it's a little bit more, allows a little bit larger and smaller numbers. The exponent is 13 instead of 11. So it says how would you store that in this fictional computer? Well, it's pretty much the same as what we did, except you have 13 bits for the exponent and 114 for the mantissa, but you convert minus 12.25 to binary. It's the same as before. This is a normalized binary, so E is still 3, mantissa is still 10001. But now the, well, it's a negative number, so you put a 1 there in the sign bit. Now this is E plus 4095, so that would be 3 plus 4095 is 4098, which is in 13 bits, 1, blah, 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 10. And then here's the mantissa, and it looks the same as before, except you got more trailing zeros. If you convert this to hexadecimal, you've got a first 4 bits converts to a C, the next 4 0, 0, 1 0, 1 0. That would be 8 plus 2 is 10, which is an A. And then you got a 2, and the rest are 0. So this is the answer in binary, which is all they asked for. And this is the answer in hex. But it says approximately how many decimal digits of accuracy does this computer have? And the relative precision is 2 to the minus 114. And for some reason I don't have the answer written here, but just have to convert 2 to the minus 114 to decimal. Actually, if you try to do that in your calculator, it'll underflow because that's too small a number. But I just multiply the 114 by 0.301 because that's the log of 2 over log of 10. So I use a little trick to convert it, and so it comes out to about 34. So the answer is about 34 decimal digits, so it's about twice as accurate as double precision on this fictional computer. And here's another typical question over section 2.1. There's 2 fictional computers. The first one has, they're both 96-bit words. First one has one side has 11 bits for the exponent, 84 bits for the mantissa. The second one has 25 bits for the exponent and only 70 bits for the mantissa. Which computer can handle larger numbers? Well, that would be B, because it has more bits for the exponent, so it can handle larger exponents. So its overflow and underflow limits will be much larger. They'll be huge. Which one's more accurate? That would be well, that would be A, because it has 84-bit mantissa, whereas B only has 70 bits. So basically B has given up some accuracy in exchange for being able to handle larger numbers. And it says approximately how many decimal digits of accuracy does this computer have? Well, 2 to the minus 84 is about 10 to the minus 25, so basically 25 digits approximately, the more accurate one.